In this video I will show you in an experiment what happens when you connect several resistors in parallel to each other, and we will look at how current and voltage and also the brightness of light emitting diodes behave and how this is related to the size and configuration of the resistors which you choose. And this video is the introduction to a short series on Kirchhoff's first law, this famous junction rule which you might have heard of, and it explores experimentally what we will later in later videos take a look at in more theoretical detail and also from a physical viewpoint. And as always, in this video there's going to be a summary of the most important facts for you at the end, so stay tuned in any case. And my name is Andreas from The Fearless Engineer, and here we go. Okay, so before we start with the actual experiment, let's take a look at the measurement setup here. On the left you can see two multimeters which are set to measuring voltage on the left side and measuring amperage on the right side. Normally you have two distinctively colored cables, one black and one red, which you connect to your multimeter. But to make it clear which multimeter is hooked up to which part of the circuit we're going to look at shortly, I connected the voltage measurement to the red with the red cables and the amperage measurement with the black cables. Now let's take a look at the circuit here on this breadboard. We have made a previous video on how a breadboard is structured. So let's start with the left side with a negative power rail where the battery is connected to. Let's follow the path of the electrons through the circuit, which is not complicated. It's an unbranched circuit with a few components within the path of the electrons. Now they flow in here, they follow down this column here until they meet this connector. This connector is hooked up to one of the black crocodile clips, which leads into the right multimeter. The electrons flow into here. This one is set to measuring amperage. They flow through it. The display changes according to the amperage. Then they leave the multimeter through this black cable here, and they re-enter the circuit through this black crocodile clip, the second one here. Once they have done so, they reach row number 10, which is connected along the path which I'm showing here with my pair of clippers. And once they enter here, they arrive at the left leg of the light emitting diode, the LED. They flow through the LED depending on the voltage drop, and also we're going to see shortly whether this lights up at all or whether it's bright or stays relatively dark. And once they have passed through here, they reach the right side where they meet this resistor here, which is also connected to one port of the multimeter to measure voltage drop. So this one here. And once the electrons have reached this point, they flow through the resistor and reach the other side. And the other side is connected to the second measuring port of the voltage meter. So we measure the voltage drop across the resistor here. And once the electrons leave the resistor, they flow into the second power rail, the positive power rail, which is not yet connected to the battery. So this is a simple unbranched circuit. Enter here, flow through the measuring device for current measurements, flow through the LED, flow through the resistor, measure the voltage drop across the resistor, flow back into the battery. And the idea is to show what happens once we connect a second resistor to this entire setup here. In order to make it clear what we have here, let's remove this first resistor here from the actual breadboard, and let's make a resistance measurement. We can reuse the right multimeter to do this. Let's set it to ohm and then connect another pair of cables to it. And by using these two measuring tips here, let's put it onto the breadboard, we can measure the resistance of this device here, which is at 0.984 kilo ohm. So this is a 1 kilo ohm resistor, and what's missing to the full kilo ohm is due to the tolerance of this resistor here. Now we have a second resistor which we're going to use as well in the second part of the experiment. It's this one here, and if we measure this in the very same way, we can see that this only has 150 ohms. It's a much, much smaller resistor. But in the first part of the experiment, we're going to use the larger one. So let's reconnect it as it was before. COM port, amperage measurement. The larger resistor goes to the side for a few seconds. Let's reconnect the first one. Actually, this is the smaller resistor here. This is the larger one. And now let's hook up the battery. Please observe the LED once I connect, and also what's happening in the multimeters here. As you can see, the LED starts to glow. It's a very faint glow. And let's reset this to amperage. And what you can see on the display here is a voltage drop of 6.77 volts across the resistor and a very, very small current flow of only 0.007 amps through the LED, which is why the glow is so faint. Now, in the second part of the experiment, we're going to insert this second resistor here, the smaller one. And the question to you is, what happens once I connect it in parallel to this first one? Is the current going to stay similar? Is it going to drop significantly? Is it going to increase even? What about the voltage drop? Is the voltage drop going down? Is it going up? Is it staying roughly the same? What's your idea of what's going to happen? Maybe pause the video and think about what will occur once I connect this the second resistor. Okay, now let's hook it up into the circuit board here. So now the two resistors are connected in parallel, and once the electrons arrive here at this junction point, they're going to branch into two different directions. A few of them are going to flow through this rightmost resistor here, and the other ones are going to flow through the left resistor. And the question is, what happens now? Let's reconnect the battery. And as you can see, the LED glows significantly brighter than before. And when we take a look at the displays of the multimeters here, the voltage drop has not changed that much at all. It's now at 6.3 and something, which is a little bit lower than before, but the change is not that dramatic. However, the change we can observe in the current flow, this is really a strong increase which we can observe compared to the setup when we used only a single resistor. Before we were at 0.007 amps, now we are at 0.049 amps, which is a dramatic increase in current flow, which you can also see visualized in the brightness of the LED. Now, this behavior is actually governed by Kirchhoff's laws. There are two laws postulated by Kirchhoff: Kirchhoff's first law, Kirchhoff's second law, and this is the so-called junction rule, which governs the behavior of the electrons flowing through this circuit here. And by using Kirchhoff's junction rule, we can compute, depending on the size of the resistors here, which amount of current is going to flow through the left branch and also through the right branch. Also, how the overall resistance is going to change. As you can see, the current flow has increased. This means adding a second resistor has decreased the overall resistance here, not increased, but significantly decreased. And we can derive very easily and pretty straightforward the amount of decrease which the second resistor brought forward here. We're going to look in the next videos at how we can arrive at the formula to compute the overall resistance. We're going also to derive the formula for computing the current flow through these resistors here. This experiment was to show you what happens when we branch off a circuit into several directions. Up until now, we only have looked at unbranched circuits. So this is a first glimpse of what's going to happen once circuits become a little bit more complex. Now let's quickly summarize the most important findings from this video here. We have seen that if a significantly smaller second resistor is placed in parallel to the first one, the current through the light-emitting diode increases strongly. And this increase in current is inversely proportional to the value of the resistor which we have connected. And the voltage drop across the resistors which are connected in this parallel manner, this decreases slightly, but not in the same proportion as we have seen the current decrease. And lastly, the observations and measurements we have seen here, they follow Kirchhoff's rules, which are called junction rule, and also the loop rule, which you might have heard of before. And in the upcoming videos, these relationships will be explained from a physical viewpoint and also from a mathematical viewpoint. If you have any questions regarding this video here, don't hesitate to drop me a comment down below. Also, if you have ideas for future videos, leave them here. This is all from me for now. I wish you a nice day. See you next time here on The Fearless Engineer.